So, you just moved out this cap by turning it. Do you remember how many turns you just made to remove the cap completely? Also, why is it so easy to remove this with my hand but not these? So this cap is based on the principle of thread, which essentially has a helical part wrapped around a cylindrical part. The helical part creates linear movement from rotary motion. This understanding is such a miracle because it's just one of the many mechanisms that translate rotary motion to linear motion. In mechanical world, we like rotary motions because things that rotate can be easily moved through either mechanical or thermal means. In other words, we can use different forms of energy to convert to mechanical energy by using rotary motion. This transformation of energy to mechanical rotary motion allows us to automate things and therefore create machines and scalable processes. Here are some additional examples of linkage designs that transform rotary motion to linear motion. I'll link here for the original creators. You can check those out to understand the linkage motions. Let's go back to what I was asking earlier, the number of turns and why is it hard to rotate some things more than others. We do need to get to some fundamental concepts to answer these questions from a theoretical standpoint. If you look at the cross-section of screw thread in either this bottle cap or machine screw thread, this trapezoidal thread form is what you usually see. The same trapezoidal thread form applies for both external and internal threads. We'll see more well-rounded edges in caps of the water bottle that you use or the pill bottle that you're taking because they're manufactured with injection molding instead of machining. Thread shapes, however, used to be like a V shape as shown on the right. They have been modified to trapezoidal shape over the years, and that has allowed longevity in screw threads. We've come a long way to agree upon what standards to be using. Most parts of the world use ISO standards, while US and Canada use UNS. And in each system, there are both fine and coarse threads. Nevertheless, the 60-degree thread angle remains the same across all systems, as well as the relation between major diameter, pitch diameter, minor diameter, and pitch distance. I'm not going to go over the equations to calculate each parameter because you can get the idea from looking at this diagram, and most likely you'll be referring back to NC specifications to get those parameters spit out for you when you are checking specs of the screw that you're interested in. When you look at the specs of a screw, for example, in ISO standard, you'll see something like this. Here, M4 refers to major outer diameter 4 mm and 0.7 refers to pitch diameter in millimeter. As for UNS system, which we see in the US, you'll see something like this for thread sizes under a quarter inch. Here, number 8 gives you some clue to major outer diameter dimension. There is this magic equation which you can use to calculate major outer diameter from that number. But for sizes of 1/4 inch and over, major outer diameter is essentially the same as what you see on the screw thread. So 1/4 inch means 1/4 inch major outer diameter and so on. Just like ISO system, the second part gives you information about the pitch, but rather it gives you number of threads in 1 inch. So, for example, 32 means that there are 32 threads in 1 inch. So if you want to know pitch distance, you need to divide 1 inch by 32. So why am I telling you all this standard? Because it does give you a quick to learn how much an object moves by just looking at their specs. So for example, if you want to move something really slowly, you'll use a smaller thread pitch and a larger thread for bigger movement. The same understanding is used in power screws, which are used to transmit loads. You may have seen this in motor drives with lead screws or power jack. Lead length is exactly the same as the pitch that we just talked about. It's basically the linear distance that is generated from one rotation. This lead length is one of the things that also defines the linear resolution of your system from one rotary turn. There will be a net which is used to carry your system that needs to be transmitted. The lead screw will experience friction as it is rotated to transmit the load. High friction is major downside of this threaded transmission. Material choice of your net and lead screw is important to have low friction coefficient. Here's another example with power jack and lead screws. By rotating this horizontal helical gear, you'll translate this vertical screw up and down. There will be thrust collar mounted at the top where your load sits. The collar essentially decouples the rotary motion of the vertical screw from the stationary platform. Now that you understand application of power screws, you might be asking, are they any different from the first type of machine screw that we talked about? They work the same, but specs are slightly different. In power screws, there are 3 thread configurations: square, acme, and bed dress. Yes, acme threads do look similar to trapezoidal thread shape found in ISO and UNS systems that we discussed earlier. They're also the most commonly used threads in the power screws. They have easier manufacturability compared to square threads because they don't require perpendicularity. They work best for loads in both directions, whereas the bed dress threads work well for load in one direction only. However, square shapes are the most efficient and strongest because they don't have any radial load between screws and nuts, unlike the acme threads. The main thing that's different about acme thread compared to ISO and UNS thread is their thread angle. It has 29° instead of 30° like in the ISO and UNS standard. So that makes acme threads a little bit thicker and much stronger than standard machine screws, making them better candidates as power screws to transmit loads. Let's go back to application again. We talk a lot about achieving translation from rotation. Do you think your load stays locked in this position when there is no applied rotary motion? So this answer depends on this equation shown right here. You can actually calculate whether lead screw is back-drivable or self-locking. You do have to know your coefficient of friction in the screw gem net and do calculations on the screw geometry that is based upon pitch length, diametral pitch, and thread angle. And your system will self-lock if your coefficient of friction is greater. The spec sheet from the vendor should also be able to tell you about it. However, in some applications, you would actually want to reduce this friction to increase efficiency and power output. So to combat high friction seen in lead screws, ball screws come in pretty handy. Ball screws contains a train of balls in the nut that creates a rolling contact with the lead screw and reduces friction. It is therefore back-drivable and would require a brake to lock in the position. Lastly, let's get back to my other question. What determines something to get unscrewed by hand versus a power tool? Your applied torque needs to overcome friction that was resulted from the existing holding torque. So let's talk about torque and screw a little bit here. Torque determines how much turn capacity is generated by the force applied at a perpendicular distance away from the central axis. That perpendicular distance in a screw is essentially 1/2 of diametral pitch. You can go back up my video to refresh what diametral pitch is. So just by knowing the screw size and specs information, you can have information about maximum torque or clamping force the cap or the fastener hardware can provide without it getting broken. If you torque more, you'll get more clamp force. That means if the screw has 2 times larger diameter, you'll get 2 times the torque, and thus the holding downward force would be higher. We can always torque more to ensure that the force to clamp down and unclamp your system is high enough. That way your system is resistant against external vibrations and your bolt can still take a majority of the loads. So the amount you need to disassemble your screw and nut depends on the existing holding torque. What about power screws that we just discussed earlier? How would you calculate your torque to translate your system? If you unwrap rotation of the screw thread, it would look something like this. And you can start drawing a free body diagram to determine this big force F to overcome friction force little f. From this big F, you can calculate torque that you must apply to lift or move your system left or right. If you do more derivations, you can represent this big F in terms of existing load P, friction coefficient mu, and lead length big L. In some systems like power jack, there will be additional friction between your moving part, the lead screw, and the stationary part, thrust collar. So you will need to overcome friction there as well to move your system. So that's what the second part in the equation is. So to recap, we talk about screw specifications, torque, and how its mechanism is fundamentally used to transmit motions. There's still more to how screws are used in many mechanical designs and assembly of various mechanical systems. And you should check out this excellent video from Tarkka on screws as fasteners, which I will link right here. I'll see you again in my next video.